let's now develop some classes for the composite pattern. So let's say this is the simple expression hierarchy we assume, and you should really review your lecture notes on the composite pattern. So let's say we want to model the structure for a simple expression like a 2 or 3 or 2 plus 3. So the 2 and 3 are the constants, so these are the base cases for some expression concept. And the addition over here is the only way we can build up expressions recursively for as complicated as we like. We can say 2 plus 3 plus 4 plus 5, okay? And then the pattern we follow is to say we use the multiple inheritance in IFO. So we got addition here, and then addition is a subclass of both expression, which is a common superclass with constant. And also addition is also a subclass of the composite class. And we make composite class just in this case, just to say composite simply got left and right as expression. Okay, or we can make it generic. Okay, we can try different things for this particular composite pattern. I'll try to make it as usable as possible for you. Let's say we try to make composite generic. Okay, let's now go to our IFO Studio here. From the previous tutorial, you should have a cluster called structure over here. Okay, let's create a new class over here. Let's call that expression. And the expression class should be deferred because you should not be able to create an object of dynamic type expression. Okay, that's only there for you as a static type. So you can have polymorphism being either constant or addition as the dynamic types. Okay, let's create. Okay, it's deferred. And then we also need to have also two classes that will inherit from the expression class. One is constant. Okay, for the constant class, we'll say inherits from the expression. And then also, if you remember the structure here, we also got an attribute for the constant being the value. So for every constant, you know what the value is. For example, 2 or 3. Okay, so feature over here, let's say also create and make. Make over here the constructor. Okay, that's the standard name. And over here, let's say attributes, and then we can have some value here. Let's say integer constant, and also feature constructor. And then here we can declare the make. Let's say the make is going to initialize the attribute value with some initial value. So we can say make over here. You can say new value also of type integer, and then we can say do value is assigned to new value. So here depends on what you need. If you don't want to have any negative value, what you can do is you can put some precondition over here. You can say require, and then new value should be larger than 0, for example. And at the same time, you want to also say, we can say we want to make sure every constant object, for the constant object to be valid, that means its value attributes, the value must be always positive. Okay, you can also put an invariant over here. Okay, in this case, I can say the value is larger than 0. That's a class invariance. Class invariance simply means for your particular object to be valid. So what does it really mean? What should be the valid state or legal state for your object? For constant, let's say we assume the value itself must be positive. So 0 cannot be good. -1 cannot be good. Only 1, 2, 3, 4, and onwards should be valid. Okay, let's make that assumption just to illustrate that how you can develop the invariance over here and to make sure when you are trying to initialize your attributes, you don't violate the invariance. Okay, you can see that if I take this out over here, and that means if I say make -1, then I will actually allow this assignment initialization of value to be -1 to be allowed. In that case, I will get an invariance violation. Okay, that's why I should really put some required clause over here. Okay, just a brief review of the decide by contract contents we talked about before. Okay, so now let's compile over here. So now everything is okay. So now we are done with the constant class. Okay, let's now go to the addition class. In addition class, for now, it just inherits from expression. Okay, and then we'll also do composite in just a moment. Okay, add a new class over here called addition. and it also inherits from expression. And then we would say create and make and feature, okay, over here. Let's say for the feature over here, we can say, let's not follow, okay, let me just show you something that's slightly different from what's really shown in the architecture diagram, okay? What I would do is, I will simply say the addition is going to inherit from expression and also inherits from composite. But the composite is going to be a little bit more general for code reuse for other applications. So rather than just having left and right, we're going to have children and add child. Okay, I'll show you, okay, in just a moment. So now over here, we'll say feature, okay, and then we'll say left and right. Okay, let me just put a constructor first. Make over here, and then we might have to take some argument over here. I'll do that in just a moment. Okay, let me just declare that first and make sure everything compiles. Okay, before I can do any developments on this expression class, let me also add a composite class. Okay, so now let's add a composite class under structure cluster called composite. And the composite, let's make it generic. Okay, which means the composite can be a composite of expression, it can be a composite of equipment, or it can be a composite of person, depending on which class you need for your application. So let's just make it as general as possible for code reuse. So remember, code reuse also is a very important design principle. Okay, so now class composite over here, and then we can say create and make. Okay, actually we don't need create make because composite should be a deferred class. Okay, I'll show you why. Because we don't want to really create any dynamic type of composite. Composite is only the static type. Okay, so now here we'll simply just declare the feature. Okay, let's say attributes over here, children. It's gonna be just a linked list of G. So the G over here refers to the G over here. Okay, they are the same. And also feature over here, we can say command. Okay, now how do we add new child? So in general, the linked list can be arbitrarily long. So we can say add child over here, and then we can have new child, and also G. Okay, over here I can say children dot extend, and then new child. Okay, I just compile. Okay, everything compiles. Now let's go back to the addition over here, and then we'll say that's multiple inheritance. Let's just go back to architecture diagram. Addition inherits from expression. Also addition inherits from composite. However, you should notice that addition inherits from composite. Composite has a linked list of children, but we have to say in the addition level, we want to say very explicitly using contract to say the number of children we have for this particular addition here is only 2. It cannot be less than 2, it cannot be more than 2. It must be exactly 2. And the way we specify this validity of addition objects is by using class invariants. Okay, I'll show you that. Okay, it's really worth knowing. Okay, so now first of all, let's say inherits composite. So now we have to instantiate the G for composite. So now in this case, it's going to be a composite of expression. Okay, so now if you simply say compile, okay, the reason that this is complaining is we inherit, okay, you can see variable is not properly set and attributes composite.children, which means we inherit the children attributes from the composite class. However, in this class over here, we did not initialize the linked list, which means by default it's going to be null, which is not allowed for voice safety. So you can refer to the voice safety lecture notes for why we need to initialize the attributes always. Okay, to fix this is easy. We can simply say creates children dot make. So this children is inherited. You can see that again. So we define composite of G, and then we just have children attributes at this level over here. And then because addition inherits from composite, so we want to make sure any non-deferred or effective class, make sure in their constructor there, you explicitly initialize every objects, every variable. Okay, so now we can say create children and make, compile, and everything compiles. Okay, but now we do have the add child feature available to us from the composite class. Now one more thing to do. Invariance. It is important to notice that children over here, if you see, okay, just open a new tab and then go to composite. In the composite class, you can see children is simply a linked list of G, and linked lists can be arbitrarily long. However, in the context of addition, we want to say for this particular descendants of the composite, its number of children is simply just 2. Cannot be more, cannot be less. Okay, so now we want to say something about binary operation, right? Because addition is a binary operation. So now we can simply say the children dot count. Okay, that will be the size should be equal to exactly 2. Okay, it's not compile. Okay, so now you can see that, and now in this context here, so that means whenever we say children at position 1, that refers to the left. Okay, it's pretty much like the left that we talk about in this diagram here, but we just did a slight variance to this. Okay, and also when you say children at position 2, that refers to the right. Okay, I'm going to show you how you can do that. Okay, so now let's say in the constructor for the expression here, let's say we want to initialize the left and the right. So you can see left and also the right over here, both expression. Okay, so now just compile over here, and now what we can do is we can say, because we want to make sure after the initialization, the class invariant here should be true. Think of the class invariance as the post condition for every feature of your class. In this case, the constructor also is a special feature. That's the very first one that's called by your clients. So now we can say, so after creating the children.make, so the children is at the moment empty. So now it's extended by 1 position. Children.extend, okay, left, and also children.extend, and then you can say right. Okay, let's now compile. Okay, so now we are ready to actually test this small composite pattern that we just developed. Again, this is the architecture diagram. Okay, now let's try that. Let's go to test structure over here. Let's have a Boolean test. Okay, you can say test expression structure, and let's put a Boolean over here and do. Okay, now let's see what we can do over here. And what we will do is we'll show you, how about this? I will do the comments in just, let's do the comment here. Let's just copy and paste the feature name over here, colon, and followed by some comments over here. So we can say test, let's say construct. Let's say we want to do something like this, 2 plus 3 plus 6. Okay, of course, parenthesis is over here just conceptually. Okay, so basically we're going to build an addition overall, and the left for the addition is actually just another addition whose left is 2 and whose right is 3, and the very top addition there we just talked about, the right should be just 6. Okay, so now let's see how we can build that. So what we can do is local over here. So basically we got, how many expressions do we have? We have 2 and 3 and 6, the constants, and also 2 additions over here. There's the first addition at the top, and that's the addition at the second level. So we got in total 5 different expressions. Okay, I'll say E1, E2, E3, E4, and E5. And they are all expressions. Okay, over here, and then I will show you one way to add the expression into it, and then you will see there was some limitation. Okay, notice one thing. You can see that the static type for all these expression variables are expression, which means only the features defined in expression can be called. At the moment, what features do we have? You can see if you go back to expression here, we have no features over here, which means the static type is good because polymorphism will work. We can create dynamic type of either constant or we can do addition. However, you will see what I mean. Let me show you. So now what we can do, first of all, let's say let's do the constant first. Let's call this E1, this E2, and this E3. Okay, we can say creates constant E1 dot make and then 2. Okay, similarly, we can also do 3 and 6. 3 and 6. Of course, we're gonna change that to E1, E2, and E3. Okay, so far so good. However, notice one thing over here. Can I say anything like result is assigned to E1 dot value? Because I'm thinking that if I go to the constant class over here, you can see we do have some attribute value over here. But can we make that feature call over here, E1 dot value? Okay, now if I try to compile, apparently I cannot. It says unknown identifier value over here. Okay, let's expand the error message a little bit to see what the compiler tells us, but you should be able to judge based on what we learned in the lectures about polymorphism. You can see that over here, you can see the value over here is not defined in the expression type. The expression is a static type for E1, right? Expression over here is declared as a static type for E1. And now we are trying to say E1 dot value. However, value is not a feature of expression. It's only a feature of its descendant class, like here. So value is not defined over here at this level here. It's defined at this level. That's why it does not compile. Okay? So there are two ways for you to fix it. Okay? You can either try to do a cast. I'll show you the cast version over here. And then I will comment it out. Okay? You can either say we can do a cast, check, attached, constant, and then E1 as C1, constant 1. Over there, you can say result is assigned to, and then you can say C1 dot, now you do have value defined. Value is equal to 2. For example, that's what you can do. Okay? If you really don't let, this may not be so desired because you had to do cast always if you want to call the descendant class specific features. Okay, so in this case, it's completely up to you. You can either do this or we can simply just change the static type of the expressions. Okay, it's completely up to you. Okay, so now let me just comment. Let me just only leave E1 as the expression. So you always see that you always have the need to actually do the cast. And similarly, if we also try to say creates, let's say E4 as addition. In that case, also the add child would not be available for us either. Okay. Okay. Let's now do the following. What I will do is E1 is here, and E2 and E3 will be constant. And also, if you like, I can even just make it C2 and C3. Okay. And also addition 1, addition 2. Okay, that's what we can do. Okay, let's compile first. We got some syntax error here. Okay, that should be just equal. All right. Check result n. So now here, what we can do is for E2 and E3. Okay, so now we should just change them to C2 and C3. And because they're constant already, so we don't really need to put this part here. Remember, in IFO, if the static and dynamic types are the same, you can abbreviate the notation like this. Okay, let's compile over here. Okay, everything compile. Okay, so that's about creating the constant. Let's also create the addition. Let's say this addition over here is A2. Okay, the second level. Okay, so let's do the A2. So we can create addition, okay, A1 dot make, the left and the right. The left should be this constant here, which is 2, and that'll be E1. and then the right expression over here should be 3, which is C2. Okay, so I'm going to put C2 over here. Okay, now what about this second addition over here? Let's call that, sorry, I meant to put A2 over here. Okay, that's second level addition, just to make the naming a little bit more informative. Okay, what about this addition over here? That's a top level. In that case, I would say creates A1.make. And now the left should be the entire A2, right? And then we should have the right-hand side, which will be the constant C3, which is 6. Okay, let's put C3 over here. Okay, compile. Okay, let's do some quick assertion over here. Okay, so now what you can do is you can now say, so now we don't need to do any cast because static type is already specialized enough. Result is assigned to A2.left. Okay, I should declare something over here. Okay, so what I would do is you can say result is A2.children at position 1. Okay, is equal to, okay, let me just explain this. You can, of course, you can always refactor your design to make the interface to your satisfaction. If you go to the addition class, you can see that since we are reusing the composite class, which is completely general, in the sense that the number of children is arbitrary. And now when we adapt the composite to our specific context, we simply say the number of children should be equal to 2. But how do we refer to the number of children? The children one by one, the left and the right. So one way to do it is you can simply still use the children feature over here and then say children at position 1 for the left and children at position 2 for the right. That's one way to do it. Or if you like, we can trade the space for clarity. You can also say feature over here, some attributes, okay, or queries. How about that? Okay, so now we can waste a little bit more computing resources by running a query, but we can actually also do the same. We can be a little bit clearer in terms of asking the question for the addition. Okay, so what we can do is you can simply say left over here is going to be expression. Okay, and now remember the uniform access principle. Even though we put queries here, but it doesn't mean the left should always be a just query. You can make an attribute as well. I'll leave that to you. Okay, so now you can say result is simply equal to children at position 1. Okay, similarly, let me just copy and paste this block of code, and then I can say right, and then children at position 2. Okay, in that case, now whenever you want to refer to, let me just see what the syntax error is. Okay, I'll just do that in a moment. So now addition here. Now, whenever you want to refer to the left child, you got two options. You can either call left, or you can say the addition dot children at position 1. Either way, so now they're synonymous. Okay. Okay, so now let's say A2 dot. Let me just compile again. Okay, otherwise it wouldn't show up in the drop-down menu. Okay, compile. Make left and right. Oh, because I got left and right being the names of the queries, so they're global. So I should avoid the name clashes. What about L and R? Okay, L and R. Okay, let's compile again. Everything compile. Let's go back here. So now let's uncomment this. I can say A2 dot left. Okay, so in this case, it's gonna be the expression over here, and you can see that if I simply say dot value, it wouldn't compile. Okay, again, it's very important for you to see why this is the case. Okay, you can see unknown identifier value. The reason is if you go back to addition over here, what's the return type for left? It's actually expression, which means the static type for the left is actually expression, but its dynamic type at the moment for A2 is actually a constant. Remember, we actually add E1, and E1 was created as constant over here. That's a dynamic type. So in this case, we really have to do a cast. Okay, because the return type for the left is always an expression because we simply don't know how complicated the left and the right child would be for any arbitrary addition. Okay, so this is unavoidable. Okay, what I can do is I can do the following. I can say check over here. I can say A2, let's say attached, and then I can put a constant over here, and then you can say A2 dot left is A2 left. Okay, how about just that? Okay, it's a constant. And then we can now say, so the left-hand side must be like that. Okay, the left-hand side must be a constant. So now we can say A2 left dot value over here is equal to, in this case, should be 2. Okay, that's a constant over there. And then we can also do another cast. Okay, let's do another cast. You can just do another one over here. Okay, let me just do it separately. Okay, otherwise it's a little bit messy. And then we can say check result end. Okay, let's do the right-hand side for A2, which is C2. Okay, so now in this case, what we have is A2 dot right is A2 right. And then in this case, A2 right should be equal to, right, 3 over here, right? Okay, so now let's put 3 over here. Okay. Okay, let's compile. And then we also have check result end. So now after this, we also got create A1.make and then A2 C3, right? So now we can also do something similar, okay? To really make this a little bit better, so actually I will leave that to you. Exercise. Check that A2, that A1 after cast, A1 the left is an addition whose left is, so addition A2, right? Addition A2 whose left is 2 and right is 3. Also, A1 dot right is C3. In this case, C3 is simply 6. Okay, I'll leave that as an exercise for you. But you can just do the same result check and also check assertion over here. I'll leave that to you. Okay, just to save time on the video. Okay, so now we are done. So now let's just go back. So this is the very first test we did on the composite pattern. So now if you go to the application over here, so now we should have one test to be run. Okay, let's try. Run workbench system. Okay, we don't have anything here. I may have to, okay, let's see this. I may have to, first of all, go to test structure over here. I need to add a test. Okay, I forgot to do that. Okay, let's go back to the test structure over here and say add Boolean case over here and then put the reference to the test. Okay, like that. Compile. Okay, let's go back. Okay, and then let's go back there. Test application over here. Okay, let's try to see. Run workbench system. We still don't have that. Okay, let's see what's going on here. Compile and then run workbench system. Okay, we may have to put the run espec over here. We may have to. Okay, let me just try. So now if I go to test structure over here, so we may have to say run espec over here, and let's compile. And then run workbench system. If not, how about show browser over here? Okay, compile over here, and then say run workbench system. Okay, that works. Okay, at least we got something brought up. but I do have some assertion failure. Why don't we try to debug? Okay, if you say run over here, let's see what's going on. I got something over here. Okay, so now the value is not set to 2. Okay, so now I got some check violation raised. Okay, so let's see what's going on over here. Okay, I created E1 as a constant, and then I say result C1 is C1 the value is equal to 2. Okay, why don't we try? C1 the value over here is 2. Okay, and now this one should work. Constant, and then E1 was created as a constant over here, and then as C1. Okay, and then we have result is assigned to, result is, okay, I know what's going on here. Okay, let's stop that. Okay, let's go back here. Okay, let's go back to test structure over here, and then we should say result is assigned to. Okay, because remember, result is the result for the return value for this Boolean test query. So we want to make sure we assign some intermediate value of either true or false to signal what's the intermediate result for the test query. Okay, that's something I forgot. Okay, let's now say compile. Okay, and then we actually want to make sure I say then. Okay, maybe that's why. Okay, and then compile. Okay, make sure you understand the syntax for the typecast attached, and also don't forget overall is a check assertion, so that's why you gotta have then over here. Okay, compile and then run. Okay, now everything passed. I want to just double check one thing. We want to make sure we only run the minimum, write a minimum number amount of code. If I go to application over here, okay, so and also we have test structure over here. Okay, so here we got show browser and run expect. I wonder if I simply just get rid of this, would it work? If I say compile and then run workbench system. Okay, that'll be okay. So you just put the run expect and run show browser over there. Okay, that's what you do. Okay, and now, so what we have achieved, let's just do a quick summary. What we have achieved was we actually did a slight variance of this composite pattern here for the small expression language, where constant is the base case, addition is the recursive case, and the addition is using multiple inheritance in iPhone. It is one kind of expression, which is the recursive case, also is one kind of composite. And the composite class we did was completely generic, which with a list of children. So now that's why in the addition class, we want to do some further constraint as a class invariant to say the number of children should be equal to exactly 2. It cannot be 1, cannot be 3. It has to be exactly 2. And then we also show you some test cases, how you can build up the composite structure like this. Okay, that's something you should really study over and see. In some cases, we do have to use typecast because when we declare static type of expression, and then in that case, we want to make sure we can access the feature that are only specific to the descending classes. Also, equally importantly, if you look at the addition class, in that case, you can see the return type for the left and the right over here, they must be expressions. You cannot simply just put constant here. For example, if I put simply constant here, that's conceptually wrong because for any arbitrary addition, the left-hand side may not be just constant. The left-hand side of that might still be another addition. For example, over here, if you have 2 plus 3, and over here plus, and then 4 plus 7. In this case, you can see for this particular addition here, the left-hand side is actually this entire addition, which is not a constant, right? So that's why the return type for left must be also as general as possible, which is just expression. Now, because the static type is actually expression, that means the return value there, you cannot simply just apply any descendant class specific feature. For example, over here, you see that we could not simply just call the, let me just look for that over here. Okay, there we go. We could not simply just say A2, so A2 over here, okay, so let me just see that. Okay, we have constant, we have addition here, right? And then if you actually simply just return a to the left, okay, over here. So if let me just go a little bit further, okay. Maybe there's something I should really show you quickly, okay. If I simply say a1 dot right, okay, you can see a1 dot right in this case is actually a constant over here, and a1 dot left is actually an addition, okay. So now if I say a1 dot left over here, what's its static type? If you go to the addition here, you can see the static type is actually left, but the dynamic type, as we can see from our reasoning over here, this is a1, okay. A1 the left should be just another addition, okay. Addition means the left and right should also be available, but if you simply say a1 the left, it will not compile, okay. So now let me give you a little bit, okay, let me just help you a little bit further. So you can say check over here, let's do a cast check, and then you can say check attached, and then you can say the left hand side of a1 is also just another addition, okay. Now you can say a1 the left, okay. You can say as a1 left, okay. It's simply another addition. In this case, we can say result that is assigned to. Now a1 the left refers to this yet another addition over here, and its left hand side is actually 2, and the right hand side is actually another constant 3. Okay, that's something I will leave that to you to actually do. How to actually write the test for that. Okay, so here I can simply say a1 left, okay, dot left, okay. So now this is actually some constant. In this case, the constant comes from a2, okay. And now a2 over here, let me just see you should really draw a tree to actually to see what's going on over there. And when we first created a2, the left hand side should be e1, okay. I can simply say is reference equal to e1, okay. That's just one example assertion, okay. If you say run and run workbench system, and everything pass. Okay, so now we are done with this composite pattern here. You should really try to go over all the points I've gone over. They are kind of quite sophisticated, involving polymorphism, and also when you should do the test, and when you should do the cast, and when you should not need to. Okay, it's very important. Stay watching.